meet Barot from New York University, and he's going to talk to us about Graph-Regularized Autoencoders for protein feature learning.
Hi everybody, I'm Amit, and I'm a PhD student at the Center for Data Science at NYU. And I'm going to talk about learning protein features from interaction networks and two different ways of incorporating side information into the learning process. So I'm gonna introduce the previous work that we did in order to combine several different types of protein interaction networks into one feature representation, and then I'm going to go into two extensions of this work. One incorporating incorporating networks from multiple species into one network embedding for proteins, and the other as a way to incorporate functional information into the learning process itself. So this is the general framework that we have for predicting function from networks. So we start off with an adjacency matrix of a protein-protein interaction network, and we do a random walk on the graph of the network to get probability profiles of every node. And then we do a positive pointwise mutual information transformation on this matrix to get a representation suitable for inputting into an autoencoder, which reduces the dimension from an n by n matrix to an n by k matrix, where k is much less than n. And then we use this reduced dimension representation in order to predict the functions using support vector machines. And so what we did was previously we took several different kinds of interaction networks, so protein-protein interaction, co-expression, and six different types of networks from string database. And we did this kind of process there and predicted functions using information from all of this like multimodal source of data. And so now what I want to talk about is combining networks from different organisms in order to produce a more informative embedding. And so in order to combine different species networks, we first just start off with a block diagonal matrix of each species network along the diagonal, and we want to fill in the rectangular matrices on the off diagonal with blast similarity at first, in order to have some sense of connection between as interspecies edges. And then we use this recurrence relation here in order to, in a similar way as the random walk and positive pointwise mutual information transformation before, in an analogous way, we get representations that are continuous and not just the original network data. So we get more global information this way. And so then from these probability profiles, we get a representation that we can input into an autoencoder for dimensionality reduction. And then we use the same kind of step. We have a support vector machine for every Go term, and we predict functions from these low-dimensional features that are informed by multiple species. And so here, what I have Go terms on the side, and these are the area under the precision recall curves for all of these Go terms. And this is the annotations that we used to train was, this was trying to show how predicting function for human proteins using the same amount of training data for the SVM increases performance when you add multiple species into just the network embedding. And so we can, the plot on the bars on the right indicate the difference between the middle set of bars, which is multi-species, and the blue set of bars, which is just including human. So the multi-species includes all of these model organisms that I list at the top here, including E. coli, and mouse, and these things. And so it does a fair bit better. And so now I want to switch gears a little bit into the second kind of way that we're incorporating side information. And so this comes from semi-supervised learning, where we're trying to, we have a goal in mind where we want to enforce samples in the feature space to be similar if they're similar in the label space. So if two proteins are functionally similar, we want to constrain the model somehow, the autoencoder portion, to produce features that reflect this functional similarity. And so how do we do this? We add a cost term to the reconstruction cost of the autoencoder. So in addition to the reconstruction, we have a regularizer that enforces this penalty. So in the inside of these parentheses, it's so the F matrix represents the features extracted from the middle layer of the autoencoder, where we're going to use those for function prediction later on. But we have a measure of similarity by the dot products between each feature vectors, between all the feature vectors in the data set, and that gives us an n by n matrix inside this sigmoid. And then the S matrix is the external similarity measure that we get from either Go or Brenda or any measure of any way we can compute similarity between two proteins based on function. And then the M part of this is just a masking term where if either I or J proteins are unlabeled in the functional category that we have, it just makes the cost function 0. So we don't have those samples influencing the cost function in this way. So only the reconstruction cost is affecting it. And we test this on the Brenda terms, the top 7 Brenda terms. And we have in the red bars is without this regularization, and the orange, purple, and blue are various strengths of this regularization term. So we can see that there is like an optimal strength for this term, indicated by the purple bar, that we can select and take a little bit closer look at. So this is the same style of plot as before, where we have the difference between two models' performances for individual terms that we're classifying for. And the similarity regularization, where gamma is 0.5, does a fair bit better on these terms. And yeah, that's all I really wanted to talk about today. Thank you guys for listening. Thanks for the organizers for having me. I want to thank also my advisors, Rich Bonneau and Kyung-Yoon Cho from NYU, and Vladimir Grigorievich from the Flatiron Institute. Thanks, guys.
Okay, so that was, I should have said, the first of our short 10-minute talks. We have a quick minute for a question while the next speaker sets up. Does anyone have any questions? No. Okay, well, you got off then. So our next speaker